guys can hear me in the back, right? Yeah, I teach 230 freshmen every week, so shouldn't be a problem. I was asked to, in the first 10 minutes, not launch into my talk and instead tell you about my kind of trajectory. So I'll do what I was asked. I got into science because there was a real energy crisis in 1974 when I was 18, 19. We had an oil embargo. I remember with my dad waiting 2 hours in line to get gasoline. In California, you could only get gas on Monday, Wednesday, Friday if your license plate ended in an odd number, and on Tuesday, Thursday, Saturday in an even number, and all gas stations were closed on Sundays. There were hostages being held from the US and Iran. Jimmy Carter started this thing called the Department of Energy, which we didn't have before that in our nation's history. So we had a real here and now energy crisis, and I wanted to do something about that. So I went to Caltech as an undergraduate, discovered a molecule totally randomly that when you went out in the sun made hydrogen from water. My boss got on cover of Popular Science. It ended up going nowhere, but it was motivating and interesting and fun. And then in the 80s, when I became an assistant professor, energy became a backwater. We had plenty of it. Oil was down to $8 a barrel. There was no funding for it, and there were no energy sciences groups or seminars. There was nothing. And so I went and did a lot of fundamental research in a pretty esoteric area in semiconductor interface electrochemistry and in scanning tunneling microscopy. I was at Stanford as a faculty member. I moved back to Southern California in 1988 at Caltech. And I was doing surface science and doing my other passion, which I claim to be the only person that can make this statement. If you have graduated from my university in the last 30 years, then you had me as a professor. Not if you're a chemist. If you've graduated, you're an alumnus from Caltech in the last 30 years, then you've had me. And that's true. That's 99% true statement, because I teach Chem 1. There has been no other Chem 1 professor foolish enough to do this class for 31 straight years. And it's a required class of all freshmen. There's only one section, only one lecture. And that means every single person has had, there are 3 people out of the 230 that'll place out. So it's 99% true that I know them all. Right? So that's a pretty interesting thing. It's a great thing to be able to say that. And I teach it in the same lecture hall that Linus Pauling taught it. And I use and update Pauling's book. And I tell them stories about how in 1925, Linus Pauling over there invented resonance structures and hybridization. So now let's learn about them and all this stuff. So that's kind of what a professor is supposed to do, right? Supposed to teach. In research, there's a pretty interesting story that I don't have time to tell you about. As I've told you, in the 80s, the energy was a backwater. And so what happened? Well, in my case, in about 2002, when my son and I every year were in Hawaii, like we still do, for vacation, snorkeling, he actually asked me why the coral was bleaching. Because it was pretty obvious even then it was starting to bleach. And my problem was I knew enough to tell him why it was bleaching. We were CO2 emitting and acidifying the oceans and making it to soda water, and that was dissolving the coral. So I told him that, and he said, well, Dad, why don't you do something about it? Okay. And I left and said, you know, he's right. Okay. So I was one of the first people to put together the nexus between energy and climate and CO2 emissions, and gave a talk that I'm still very proud of, that has been seen by live over 250,000 people. Steve Chu will tell you it's why he went to the Department of Energy. I've had just tons of people say this is their wake-up call as to why they're working in energy, because they figured out it really mattered and we had a big problem. And so Rick Smalley and I used to go around the country. Rick was a Nobel Prize winner, and I would be the warm-up act for him doing his thing. I was very pleased to be able to do that. And so I learned a lot. I would always learn about, from people I had no business knowing. I learned about the energy and economics of wind turbines. I'm a materials chemist. I shouldn't know anything about that. But I was kind of never push my own agenda, always trying to learn about both sides of the coin. And that's really been valuable for me. And then in about 2005, I took my kids' advice. We had a group retreat, and we said, well, what's a big real gap in energy systems that we could actually be working on that would make a difference, that is just something we don't know how to do now? And that's pretty obvious when you think about it. Making fuel from the sun is a big gap. We can make electricity, but it's not there at night. And if you can make fuel, then you can bridge stationary and mobility, you can store all sorts of things that are problems aren't problems. So we concocted a way you might think about doing that, and we kind of changed our research program into still doing fundamental things, but doing them with a use-inspired view of how do we meet this grand challenge. All of the details of that chemistry material science program, I'll launch into if you can take it in my second talk in chemistry later today. That's what I do most of my time with. But in the meantime, I've had the opportunity and fortune to be non-labeled. I'm not colored red or blue. And so I've interacted in hopefully an objective fashion. And I've been called to testify for both by the Republicans and by the Democrats on energy issues. That's where I want to be. I'm not labeled a pro or anti-nuke or climate change person. And that's really good. That we don't have very many of those people. And the other thing is that because of my interest in policy, I have cards because I actually know a lot about the technology. So I'm actually doing, I'm not just talking, right? And there are not too many people that are actually doing both. So that's kind of my background. There's more, but, and the other thing about that is I still feel connected enough to that I got connected in a serious way to a wonderful collaborator at Carnegie Institution for Science in Palo Alto on Stanford's campus, Ken Caldera, who's an ocean acidification climate scientist. And I just visited because I wanted to learn about that and what's really known in detail about 6 years ago. But we launched a wonderful collaboration at the time when I kept asking the question of, well, is it really true the wind always blows somewhere in the United States? Which the wind advocates say, but maybe the data should be used to actually figure out if that's true. And he had identified a weather data set that could answer this question. We built an energy system model around real data. We're now still collaborating on that. There are some very non-intuitive things that come out of that. At the end of this, I'll share with you some of those things that we're working on that are grounded in real systems data that, you know, it's pretty hard to fight data that anecdotes don't win the day. So that's another part. The third thing is that what I thought I would do for you is this is a top 10 list in my estimation of things you probably haven't heard about that are just as important as the things you have heard about. I'm not going to tell you about the stuff that, this is what I wrote when I became editor-in-chief of this journal, which I don't know what happened, except I didn't do anything to make it a decade later have an impact factor of over 30, and it's the only journal in the history of science or engineering that's a full journal that's done that. I mean, there's nothing in JAMA. So that shows you that there was this pent-up enthusiasm of a community of scientists that had nowhere to publish their energy stuff that would be in that community, and somehow this was the right place at the right time. And I didn't do anything except give my name as editor-in-chief to it, and maybe that was the right thing to do, because I didn't edit any of the papers. I just said, here's the journal and let's go publish in it. Everybody does. And when it started a decade ago, I quoted my partner in crime, Rick Smalley, energy is the single most important challenge facing humanity today. And he testified in Congress according to that. So he was under oath saying that, and it's pretty hard to disagree. He would go around and tell the story of, he would go to church groups. Rick was just fantastic at this, and ask them what the top 10 problems in facing humanity today are. And he would say war and poverty and the usual, development and disease. And then he'd say, what's the thing that we can actually do something about that's the most enabling to fix all those other problems? And if you ask it that way, energy always comes out the highest, because if you don't have energy, you can't develop. If you don't have energy, you can't refrigerate your medicines to cure disease. If we had a lot of energy, we wouldn't fight wars over oil, and on and on and on. And so when you actually ask the question that way, you see that this is what we convinced Bill Gates of, too. This is why Bill is involved. I know him. He emailed me once, said, please come up and tell me about energy. So I said, fine. So I get love notes occasionally from Bill Gates telling my group. He said, tell your group they're doing great stuff. He never gives us any money. It doesn't matter, actually. It's much better. All right. Here are my top, this is what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, my top 12 list. There's no priority in this. It was just stream of conscious. But I hope that it gives you some new things to think about, okay, that you may not have been thought of before. So after that 10 years, I'll tell you about materials for the built environment, materials in extreme environments, about what the real problems are with wind turbines. And it has probably nothing to do with anything that you've read about what my prognosis is for solar PV, photovoltaics, about low-cost grid storage, about cement and steel, carbon neutral transportation, negative emissions. You can read them all. Right? So this is what I'm going to tell you about. If you want to hear about standard advances in wind and solar and everything else, there are a lot of other people here that know at least as much about that as I do. I didn't think that's what I wanted to do with you guys today. The ground rule. Here's the built environment. We talk a lot about generation. This is the old, not right in detail now, McKinsey cost abatement curves. And things have changed since they did it. But in general, the point is that efficiency measures are still cost effective, and many of them have substantial abatement potentials. Insulation in buildings is cost effective over a life cycle analysis for as thick as you want to put it in there. You should fill up everybody's attic completely with insulation, because it pays on energy and it pays on carbon emissions life cycle to do that. There's no limit to the payback the thicker you do it. Same thing for walls, same thing for the whole building. So we talk about zero energy buildings, But we got to retrofit all the existing ones. And so there are technology opportunities in lower cost thermal envelope materials for retrofitting existing buildings that are kind of boring in the sense that the materials chemists aren't making the new record photovoltaic efficiency. They're just saving more energy by building this cheaper form of insulation than all the solar PV installed in history. And yet nobody works on that. I'll talk more about nuclear later, but I do want to, this is out of my old talk where I was giving people units, right? And laptops are about a watt, and toasters are a kilowatt, and small jet engines are a megawatt, and nuclear power plants are gigawatt, and all electricity demand on our planet's 1,000 times more than that. It's 1 trillion watts. And we do talk about the next generation of small modular nuclear reactors that would be safe enough that you could walk away and they wouldn't melt down. And the only problem is that the small modular nuclear reactor, all 3 words except for nuclear, they don't exist. So we would actually have to make them. And what people don't talk about is, even with fusion, what are you going to make them out of? When you get away from the conditions under which we can permit now with experience, the thermal and radiation environment, without 40 years worth of on-the-ground testing, how can we do the mechanical engineering and structural materials development to actually permit one of these things will last in that environment for 40 years? And if we wait 40 years to prototype and test it out, then we haven't built a real one for 40 more years, which means all those emissions are under our belt. So nobody talks about what you, if we built ITER, the $30 billion fusion demonstration reactor in France, it's supposed to last, if it breaks even and works as designed, for exactly 1 week. That's it. That'll be a success. The reason is that we have no materials that can survive that radiation and temperature environment now for longer than a week. So there's a whole lot of material science involved in these gas-cooled reactors and uranium thorium cycles of what are you going to build them out of? How are you going to qualify and do accelerated testing on a new material that's outside of our modeling and simulation experience already, that doesn't take 40 years from today to give you confidence that you can permit that and that it will be safe and it will last. So a frontier in materials chemistry and in engineering is, how do we build up the discipline fast of advanced manufacturing and qualification of new materials without having to test them for the whole commercial lifetime, because we don't have that lifetime if we're going to actually bring on any of these technologies when it matters. Here's the real problem with wind turbines. I think most people in this room, I say everybody, but probably most people know that on a given site, the best, easiest way to get more power in the high wind speed sites is just increase the rotor diameter, because the power goes like the cube of the wind velocity, and the more wind you can get, the more power you get out of that particular wind turbine. And you see wind turbine diameters have gone up and up and up, and in the United States, these kind of wonderful things, when they turn now, they can rotate 360 degrees, are 60 meters in diameter. So you can ask the question, why are they only 60 meters in diameter instead of 90 meters in diameter? And you have to make them out of a single monolithic material so they can withstand the stresses to turn this blade around. It's like a jet engine. Aircraft wing is stressed similarly. Well, the answer is nothing to do with the fact that you can't manufacture a 90-meter length material the same way you can't manufacture a 60-meter length of material. When Dwight Eisenhower commissioned the interstate highway systems, it had to be such that the longest object was an intercontinental ballistic missile, and that was 58 meters in length. And there are guaranteed bends and choke points somewhere in the interstate highway system that prevent you from shipping any object longer than 60 meters. And so we can build them, we just can't install them. Nobody ever thinks about this, right? So what do if you actually can't install them by transporting them across our existing highway system? You either have to develop a science basis to on-site manufacture in a mold these liquid metal alloys, or find a good mechanical engineering solution of telescoping like hiking poles. Or nobody thinks about this stuff because we're just kind of going down a learning curve and opening up new wind sites and doing the standard policy things. But you could have the cost of wind energy right now on existing sites if you could take those turbines and just increase that rotor diameter the way we know how to do if someone ever figured out a way to make them on site instead of having to transport them because we can't get them to where they are from where they're made. Okay. Third thing, I think that despite all the learning curves and all the progress in solar photovoltaics, that 30 years from now, we won't have a single solar panel looking anything like what we know now on our planet. It's not going to be that way. So I've lived through, I had one of the first IBM PC personal computers. It had a floppy drive, a 5 1/4 inch floppy drive. Then I had a 3 1/2 inch floppy drive. I was so happy. Now I have a thumb drive, right? You know, we had 256K of memory, right? K of memory in my first computer. This is what's going to happen here. There's no law of physics that says you have to use single crystals to absorb sunlight and move the excited states long enough to get them to make electricity. If we ever figure out when somebody does how to take polycrystalline material, just like grains of sand, and link them together so that the electrons can hop from site to site instead of stop at the grain boundaries, then you're going to go to Home Depot and buy a bucket of solar paint, and you're going to paint your roof. And then you'll put maybe it'll be on a metallized bottom sheet, you'll have a transparent top coat. And so you'll put 3 coats of paint on it, and every surface is going to be a solar panel. And we're going to look back and say, why did we ever think we had to buy this thing as this brittle thing with heavy glass and then put it up there? But you need, if you want to actually get enough solar panels installed to make electricity, say 10% of our electricity in 30 years, you need to put up 1 million solar roofs every single day somewhere in the world for the next 30 years. We don't make enough material to do that out of anything other than paper for newspapers and plastic. We don't make enough glass. We don't make enough of anything. And so to think that we're gonna all of a sudden gear up and do that, as opposed to doing what we do know how to do, which is we do make enough paint that people can slap on, you know, someone's gonna figure this out. And then it's gonna be like thumb drives compared to floppy drives. We're gonna laugh at people that use floppy drives. We're gonna laugh at people that buy solar panels as these single crystals that paid somebody to put up there on their roof. It's not gonna be that way. I'm going to talk later about the science paper that Ken and Steve Davis and I were really the co-leads on, where we asked the question of everybody's trying to get to 80% emission reductions, but what about the last 20%? Because if population doubles and we have economic growth, then in an absolute term, that 20% will be actually 50% or 60% of current emissions, because if it's 20% of where we were, but we're going to double population and double economic consumption, then that 20% is 40, is 50 or 60%, then you can't get to zero and you can't stabilize CO2 emissions. So we better talk about that. And then as part of that, before that, I'll talk later about our wind and solar studies that was kind of part of that thinking. So these were these difficult to eliminate emissions. We call them the last 20% that were really the last half. Yeah, it's renewable, reliable power. We know that renewable electricity can be the cheapest source of electricity, but only in a legacy system where reliability is guaranteed on somebody else's lunch. But you can't have that if you have a real system. So I'm going to talk in the end about our studies about, these are all the days of a given year when if you installed wind and solar with perfect transmission across the entire United States, you would still have blackouts. Because it's not true that the wind always blows somewhere in the United States. It doesn't happen according to the real weather data. And now we know for the first time what the magnitude and duration of these gaps would be. And so we can actually assess quantitatively how many vehicle-to-grid batteries would you actually need if you want to fill these blackouts by discharging everybody's car, and does that even make sense or not, and how many grid batteries would you need, and I'll tell you about all those studies later. The point of this was that the only reason this happened was that I, as a in-the-lab bench scientist, was just frustrated by not having scientific data answers to these policy-related decisions, that policy people were just throwing out assertions. And so it took me 5 years of it, every group I went to saying, is there any data? And people said, no, but we think this is the answer. And it couldn't have been both sides were right, that we just did it ourselves. So eventually I got frustrated, we just did it ourselves. I'm gonna stop. Okay. There's no battery chemistry now on the table even that can be cost effective to meet those gaps and that we've identified for that much energy needed, use that infrequently to fill for wind and solar. It's not possible within any known battery chemistry to do that. Yet, we have a law in our state. It's not executive order. We have a law that says by 2045, that's not that long from now, 25 years, all retail electricity sold in our state will be fully decarbonized. We don't have the technology to do that now. So we better, but those batteries, if it's indeed storage, can't just be secondary lithium batteries. They have to be a fundamentally new battery chemistry that uses really cheap elements like only carbon or sulfur, oxygen or iron, where there's stuff on the earth that we can get, not cobalt, in a lithium ion battery that comes 70% from the Democratic, not Democratic Republic of the Congo, which is under, this is going to be worse than geopolitics of oil. Right? At least oil is found in a bunch of countries, only some of which hate the United States. But if you only have 3 countries that have all the cobalt, then pretty soon it's not going to be very cheap and they'll have you over the logistical barrel. Right. Okay. What do you see? This is Seoul. This is a picture that I took out of the airplane wing, but I got a better one off the internet when I flew into South Korea last year. And it's pretty obvious. The only 2 things you see are steel and cement. So if you go back and look in that science paper, the stuff we worry about is shipping and load following electricity, but these are CO2 emissions right now, and steel and cement are basically as big, the stuff we don't worry about, as the stuff we worry about. Well, why is this a problem? Because as more and more people globally go into mega cities, they build buildings instead of shanties. We build roads, we build bridges, and last time I looked, they're out of steel and cement. But the chemical reaction involved in making cement is calcium carbonate, lime goes into slag, making calcium oxide, and that eliminates CO2. And those emissions are unavoidable from the chemical formula of the process of making cement. Either you are going to have to find a way to capture and bury all of those emissions on site at every cement plant, or we're going to have to find a totally new way to make cement out of a different end product, because if you make it from calcium carbonate, it's going to eliminate CO2 by the laws of chemistry. And if you make that cement a different way, we're back to that first problem I told you about. Are you going to be comfortable driving over a bridge made out of a new cement 40 years later when you haven't tested it for 40 years first? And is any city, country, or state going to permit that bridge to be built without doing the advanced science of understanding the performance of that new material without having tested it for that 40 years? Or more in the case of a building or a bridge. Yeah.
Doesn't cement reabsorb?
Yeah, and so Steve Davis has done, so it depends on if you manage and pulverize it all. So if you were to pulverize every building after 40 years and give it a high surface area, then 40% of the lifetime analysis CO2 could be remanaged by going back to the cement to the line from which it came. But you would have to make, because if you don't give it a high surface area, it's big chunks, it takes a lot longer to do that. So you would have to really think about carefully destroying and recarbonating all the concrete out of all the buildings that we obviously don't do now. Steel has two different but related issues. One is that steel is now made in these mega blast furnaces, and to get the high temperature in that blast furnace that's needed to melt the steel, you use a chemical. There are only demonstrations of electric arc furnaces, but everything is used now is the carbon monoxide blast furnace. Well, when you combust carbon monoxide, you make CO2. You do that for two reasons. One, to get the high temperatures to make the steel, but two, because you need some carbon in that steel to give it the mechanical properties, the right ductility and the right tensile strength. And it's the carbon impurities, whether or not they're interstitials or whether or not they're in lattice sites, that determine whether or not you have stainless steel, or whether or not you have high strength steel, or whether or not you have ductile steel. And these are carefully controlled by controlling the conditions of the blast furnace to get the carbon in the right spots, that then you build cars and bridges and structures out of that steel. If you're going to make the steel from an electric arc furnace, it's not going to have the same properties as the steel you made another way. And so we're back to, is anybody, even if you figure that out, going to let you build a building or a bridge out of that steel without knowing that it's qualified to last for the 80 years without 80 years of testing it? Nobody talks about any of these things, but you can't get rid of these emissions unless we solve these problems. Biofuels is well understood and talked about. I have just one take on that only some people, I think maybe people here do know about the secondary land use issues and the carbon intensity problems with it. But I'm gonna bring that anyway, because in most talks that I give on this, people don't know about that. So the amount of carbon trapped in the soil, in the first topsoil, a few inches, is greater by a factor of 2 than all the carbon and the carbon dioxide in the entire atmosphere above that same amount of soil. what happens when you till the soil and you convert from food to fuel? You release all that carbon. And so you release that very carbon that you were trying to avoid releasing in the first place. The payback time, that's a carbon debt. You can save carbon from emissions over some payback time and make it up. The payback time to do that is between 40 and 400 years, depending on the food for fuel crop you use. So if we don't find a way to fix this problem, then if you're concerned about emissions over the next 40 years, then converting food to fuel, even if we had advanced biofuels that were really lowering the payback time to 40 years, you've got this carbon debt that you just put into the atmosphere that lasts, half of it stays there for 3,000 years. So it doesn't do anybody any good. No matter what you do in advanced biofuels, no matter what the efficiency is, if you're paying this carbon debt, and it's doubled. The reason it's doubled is because most studies have shown that we have a lot of land use for purposes already, mostly to feed people. And if somebody over here converts a food producing square meter to make fuel, then all that does is somebody else cuts down a forest and grows that same food that we need somewhere else. So you don't actually lower the amount of food that you are going to produce, but now you had another land use conversion. Somebody took forests that were sequestering CO2 and they cut down those trees and they released more carbon to do that. And so this 40-year payback is really more like an 80-year payback. And we have to figure out ways around that. This is why people are talking about biochar or some way to take the carbon and basically keep it under the ground as opposed to releasing it until the soil. Here's another one we did. The Department of Energy told our Energy Innovation Hub, with, as far as I can tell, no scientific analysis, we don't know who, that instead of splitting water to make hydrogen, we need to be reducing carbon dioxide to make a liquid fuel directly. So most people marched off merrily and just tried to do that. But we asked the question of, does that make any sense given the planet we live on? And the answer turns out to be not exactly. You can phrase this a different way, which is the same answer. Why don't plants grow faster? If there's an evolutionary fitness reason for them to do photosynthesis, why don't they grow 5 times faster? Because that would be good. Well, we looked at the transport of carbon dioxide on the planet in which we now live from the troposphere through the atmospheric boundary layer, which is about 1 kilometer or 2 high, so kind of a mile high in the air, through the canopy and into both the oceans and to the land. Now, all these fluxes are known from the global carbon cycle. So there was nothing new for a material scientist here that we needed to invent. We just needed to have people like me talking to the climate scientists and carbon cycle people to actually understand what they already knew. And what we found is that there are actually data. You would think the Amazon is the most productive region on Earth, but actually photosynthetically it's not. It's the most nutrient and water cultured region, and that's corn in the Midwest where the money's on the line. And so if you look at the photosynthetic productivity per square meter of corn in the Midwest in the summer, it's sky high. And then you could look over those most productive regions and say, what measurements have been done about the carbon dioxide profile above those? And people have actually made tall towers, a few hundred meters high, with carbon dioxide detectors and measured its concentration. And it's drawn down by more than 50 parts per million in noon at the summer over corn fields in the Midwest. Well, according to Fick's law of diffusion, if corn is already drawing down the 400 parts per million of CO2 by 50 parts per million, it's not physically possible to have corn grow 10 times faster because it'll run out of CO2 to the surface of the earth if it does so. So if you're trying to develop advanced biofuels, or a machine that's doing what biology's doing, like we told us to do, that takes sunlight and CO2 and water and converts it 10 times faster than the fastest growing plant into a liquid fuel, it's not physically possible over large enough areas where you don't get advection, where you don't get wind pushing it in from somebody else's box. This is the same problem that wind turbines have. You know, it turns out that wind farms have wakes. I know this because I'm a windsurfer, taught you. What I didn't teach you is don't get behind a sailboat because you lose your wind. Well, it turns out if you actually start to really deploy wind extensively, say over the length of the state of Kansas, that you're going to take all the wind out of the velocity in Kansas, and there's nothing left for the next state. The wake effects go about 100 kilometers. Ken's group was actually analyzing them for the first time. This is going to end up with a game of hopscotch. Right? If you're a wind developer and you put all your wind farms right now in Kansas, you're not going to be able to put them east of Kansas because there's no wind. So you're going to buy land in Colorado, and then you're going to take all the wind away from Kansas, and then somebody else is going to put them in Nevada or Wyoming, and everybody's going to be fighting. The same thing happens in CO2. At only 400 parts per million, the solar flux is 100 times greater than the molecular CO2 flux coming down from the troposphere. So if you want to do biofuels over an extensive area, you're going to be taking that CO2 from the crops upstream to make your biofuels doing this. And that means no one's going to be able to grow food downstream if you're doing a good job. And so you're going to have a game of hopscotch of whose CO2 is it? Nobody ever thinks of it. Here's my view of the fuel. Yeah.
So what you were just saying about converting CO2, so it seems like the only really logical way to do it then is to capture it off some plant and you've got concentrated CO2 and that's worthwhile?
So that's worthwhile. So look, you're just right exactly into this slide.
Okay, awesome.
So my view of what fuel we should be using is that it doesn't matter. We take right now crude oil, which is a whole bunch of mixtures of a whole bunch of stuff, and we put it into something called an oil refinery. And every refinery is dynamically making every day different product mixes depending on what people actually use. We make jet fuel, we make lubricant, we make plastics, we make gasoline. We already know at world-class scale how to make, with hardly any energy loss, one fuel into another. The energy efficiency of an oil refinery in terms of the energy going in of the crude and the energy and all the products coming out is almost 90%. You hardly lose anything. So the way to think about this is there's only 3 biogeochemical cycles that have enough mass in them to support 8 billion people on our planet. And that's the water cycle, the carbon cycle, and the nitrogen cycle. There are 3 more biogeochemical cycles. They're below the earth. There's a phosphorus cycle and there's a sulfur cycle. But there's not enough mass flux in that coming up. We have to dig it and mine it. It's the stuff above the ground in the air that has enough flux to the surface of the earth that can power all these people. So you only have 3 things. And of course, photosynthesis over eons has driven with sunlight the carbon cycle. It gives us all our fossil energy, our oil, coal, and gas as the reduced carbons that then we burn and release it back into the oxidizing atmosphere that is characteristic of the last 3 billion years of our planet. Okay? That's one cycle, but it's not the only one. The second one's a water cycle. You could take water to hydrogen and then burn it and come back again. The third is you can run one of the 2 nitrogen cycles. You could run nitrogen to ammonia. You don't want to run the other one So they oxidize nitrogen because not the nitrates are bad, but the in-betweens, the NOxes, aren't so good to have a lot of around. So you don't really want to run an energy system out of the nitrogen oxidized cycle, but you could run it out of other biogeochemical nitrogen cycle to reduce. And there are lots of fights in transportation of should we have ammonia as the fuel or hydrogen as the fuel, or we already know how to convert at 90% energy efficiency any fuel into any other fuel. That's a solved problem. If I give you methane, that's how we make our hydrogen. It's called steam reforming. If I give you hydrogen, that's how we make our ammonia from nitrogen. It's called the Haber-Bosch process, and we make all our fertilizer. I can run these in reverse. I can have ammonia, I can make hydrogen. If I had ammonia and CO2, I can make methane. We know how, these are like the 3 gears that we played in the game with kids on the board. When you had the crank, you could turn any one gear and you click them together. And the only reason I don't have teeth on these gears is 3 gears grind. I've never figured out a way to make it so that they work. Okay, but that's what they are. So the only thing we need to do is to inject power via the kid with the crank into any one of these cycles. And then we're done. Because we can make any other fuel out of any fuel we have once we do that. So what's the logical thing? Well, water is a liquid. It rains to us. So it makes logical sense that we're going to inject renewable energy or solar directly or wind directly, but probably sun, into water, the liquid fuel that comes to us to make hydrogen, and then we're going to make all our other fuels from the nitrogen in the air and the CO2 in the air that we either capture with plants or we capture by direct air capture with non-biological systems. But what starts in the air has to end in the air, and what starts in the ground ends in the ground. I mean, there's no other long-term solution for the planet. So if you think about it that way, all of these kind of tactical fights aren't something we should be fighting about. We shouldn't be fighting about which fuel in the end. We should be fighting about how we're going to make any one of these fuels decarbonized in the first place, because then everything else will take care of itself. And because of what I've showed you, there's not enough CO2 transport per unit area to support the solar flux. You've got to suck it out of the air, but water rains to you, and it's much more concentrated, so there's plenty of it. That's why we work on water splitting directly by sunlight, because there's plenty of water to be split to max the solar flux. And we know that we would have to somehow suck the CO2 out of the air and then concentrate it. And if we did that, we would never concentrate it and then dilute it again over a big area of sunlight. We're going to do that in a chemical plant, where we're going to take hydrogen and CO2 and do what's called Fischer-Tropsch or methanol synthesis. There's no point in trying to directly reduce the CO2 in a dilute area from the sun. All right. More things you probably don't think about. I think some people here now do know that most of the scenarios, even my 2002 to 2005 talk, that was kind of the Paul Revere, we got to get on this problem, haven't led to enough solutions fast enough for political and other reasons that the hope of making a, quote, 2 degree C trajectory is pretty slim now. I mean, just it's pretty slim that we're going to even get there. Without all the integrated assessment models now have played the wild card joker in the deck of negative emissions, that they're realistically pessimistic, that the world won't decarbonize fast enough, that CO2 emissions in the oceans last for 2 million years, that in the air they last for 3,000 years. We're going to have that in the air under our belt. If we want to stabilize the climate at a lower level than that, we're going to have to suck it out of the air. All right. The other thing is that they don't really talk about how we're going to do that. There are only 2 ways to get it out of the air. One is let plants do it and then sequester it, X, bioenergy, carbon capture and storage. The other is direct air capture. The challenges with X are I already told you, you're going to take all this land with all this plant matter, and instead of using it for food, you're going to want to burn it to make energy and then bury the CO2 somewhere. If it works. We don't know that carbon capture and storage actually technically works. Now, by my definition of technically working, it's not the Dennis the Menace kind of cleaning job when your mom says clean up your room and you hide all your clothes in the closet and then you open it up and they fall out again, right? If you're gonna have CO2 buried underground and you're doing it for 100 years, if 1% of what you're doing leaks in a century, then you're back to where you started. That means technically it has to last with a leakage rate globally averaged of 0.1% a year for 1,000 years. Every reservoir is different. They're all the different cracks and fissures, and there's not enough capacity in the geologic reservoirs to handle even 50 years of CO2. And the geologic reservoirs means where the oil and gas has been trapped for long times, and those have cap rocks that you can put CO2 down. The problem is if you put CO2 down there, then all you do is make more oil. That's called enhanced oil recovery. And there's not enough room to handle more than 30 years. You've got to put it in the aquifers where it's going to migrate. And you do make literally Perrier underground. When you do that, you take CO2 and dissolve it in water and make soda water that is buoyant. And you count on the fact that you hope that very deep subsurface buoyant CO2 laden water won't find a crack or a fissure and won't get into the groundwater and won't go back into the air. But every single site is different than every other site, and there is no technological method that we now have that can characterize a site so that somebody can sign an environmental impact report that says, when I put something down there, trust me, 0.1% of it isn't going to leak for 1,000 years. So we don't know this works technically. It might work practically in the sense that somebody could sign a CO2 credit for it, a government would, and say, good, you buried CO2, everybody's happy. But the planet doesn't know what we're doing, it just counts the carbon in the air. So you can't hide behind this. We need to think about whether or not it really can be made to work technically. And nobody knows this. Yeah.
What about, I mean, just.
Oh, I was going to ask, can you explain how you get to the 0.1% number roughly?
Yeah, because if you're taking the flux of CO2 that would otherwise be emitted and you put it all under the ground, if 1% of what you put under the ground, if you're taking 100 years of emissions, were to leak, then that's 1% of 100 years, which is the same as what you were avoiding in the first place. It's just simple. It's 0.01 times 100 equals 1. So you're trying to avoid a flux. You do that by taking that stuff and putting it all in the bank in the ground. But if 1% of what you put in the ground leaks, then it's the same flux as what you were trying to avoid in the first place. And since the lifetime is so long, which is 3,000 years in the atmosphere, then you need to be talking about 1,000 years lifetime of your store in your bank, which means 0.1% of it can't leak for 1,000 years to avoid having the same flux as you. It's just arithmetic. Okay, good. Here's Paris, COP21. 10,000 delegates. Most people don't know what they actually agreed to, although the public press says they saved the planet. Here's what they agreed to. They resolved that countries should, not shall, John Kerry was responsible for changing the word shall to should, take actions to hold the CO2 levels below 2 degrees C. Of course, nobody knows what level of CO2 emissions correspond to what level of temperature changes. So nobody knows whether or not that's 400 parts per million CO2 or 500 or 700 or some other number. We can only control and monitor emissions. We can't control and have no measure of temperature on average on our planet. So other than the fact that we can't even measure that quantity or control it, it says that we should do that. And then they said the auxiliary goal is we should get to net zero emissions sometime in this century. But this is not legally binding. There are no metrics and no targets except self-declaration. Self-declaration of the countries is going to come up in 2 or 3 years. Look, you had to have 10,000 people agree on something. They couldn't agree on a statement, the sun rises in the east, unless it said, except when it doesn't. If you got 10,000 doctors together, they would agree that we should cure that thing called death. You know, yeah, we should stop CO2 emissions too. At least they agreed we should do something. That's the first step on the road, but it doesn't say we shall do it. It just said it would be nice. Well, whose CO2 is it? When you have a global, I've been involved with treaty verification for things that people, citizens of the world care about. Every treaty has to have a validation mechanism to see that people don't cheat, because everybody always cheats when money's on the line. So 5 years from now, all the countries are going to have to come up and say, I've met my pledge in CO2 emissions. China's going to say, I've met my pledge, and someone else is going to say, I've met my pledge. And the first question is going to be, how do we know? And the answer is going to be, we don't know. We have to trust you. Because there is now no mechanism of actually, here's the data from the Orbital Carbon Observatory OCO2 satellite. Yeah, there's more CO2 here than in the southern hemisphere because there are more emitters in the northern hemisphere and the southern hemisphere. But you've got winds and atmospheric circulation, and this is changing every hour, and the satellite only goes around low Earth orbit once every day. And the variability here is between 390 and 405, and every year the pledge might be, I cut my country's emissions by 10% from what it was, which is going to be 10% of the emissions that lead to a fraction of these concentrations. There is no way that you can use this to validate whether or not somebody did what they said. We have no technical means of validating, even if there were a treaty that said we shall cut emissions and will, we have no technical way of measuring that somebody, some country is doing what they say they are actually doing. Yeah, there could be a combination of monitoring how many vehicles and vehicle miles traveled and spying on other countries, that then we would have to let them spy on us to do the same thing, because you could assume we would cheat just like they would cheat, or they would assume that. And all countries, all treaties have to have these transparent bilateral things. And there's going to have to be some tribunal board that's going to say, we've looked at all the data and country X didn't meet your target this year, so they should be fined. How are you going to do any of this? Nobody thinks about it. Well, you can't possibly have a global carbon control regime unless you actually have a way to monitor and measure who's complying and who's not, and we don't have that now. And we don't have the ability to measure the things that the treaty wanted to control. We don't have a global climate monitoring system that, even if we controlled emissions, let's suppose we got into a 450 part per million trajectory and the climate models weren't perfect. They're not perfect. There are 6 major climate models. They differ from each other. That means we know at least 5 of them are wrong. We just don't know which 5 they are. There is no guarantee that if we followed a 450 part per million trajectory that we wouldn't still melt glaciers, or maybe not at all. There's no guarantee that if we followed that trajectory that we would be at a 2°C path and not a 3. It would be pretty nice if we actually had a global climate monitoring system so we knew what we were doing to our planet. We don't have that now. There is no, other than reporting stations, which typically have biases because they're at airports and cities, and the temperatures are over the hot tarmac as opposed to in the shade. There's no historical basis to know whether or not we really are going to be doing something much worse than we anticipated or not as bad as we anticipated. So it would be pretty nice if we actually had a way to measure with a scientific baseline what we're doing so we could change it. Everybody talks about the air. Remember where I started this whole thing? I started this whole thing in the oceans. Almost nobody talks about the oceans. These are from Ken, I'm almost done. This is Ken Caldera again, and this is a map of just from pH. You don't need any fancy climate models to do this. This is just when you take CO2 and put it in the air, by Le Chatelier's principle, some of it dissolves in the water, and there's an equilibrium constant there. Okay, by freshman chemistry people to graduate had better be able to solve this problem. Right? Now you have to know about ocean transport and mixing somewhat, which we know somewhat about. So within this model set, this is data on the aragonite scale of where historically on our planet the temperatures and CO2 concentrations have been right so that coral reefs will survive. This is where we find them historically, and this is the range of pH and temperature where, yeah, a few hundred million people's livelihoods depend on coral reefs regardless of your economic value of what you want to do with them. None of the integrated assessment models have a charge of CO2 to figure out how much it's worth to save coral reefs. MasterCard says some things are priceless. You can decide what you want to do. But at 380 parts per million, that's Ken's map. At 450, that's Ken's map. And we are blowing through 450 by the time you guys are my age, and that's Ken's map. And that will last, we know from volcanic eruptions, for 2 million years. So if anybody feels really good about that, it's pretty hard to say, I think this is okay. But we don't understand very much about the ocean impacts of, other than this simple pH thing, on fishing, on food, on all sorts of other things to do with the 3/4 of the planet that's water and not air. And I wanted to bring that up because it was one of my top 12 things that you probably don't talk about very much. And yet when I put these slides up, it's pretty hard to forget them. Okay, finally, I wanted to get back to that, what the Caldera group and a couple people in my group are doing on this renewable energy issue. The thing I think that's interesting, really interesting about it are two things. One, it wouldn't have happened unless you had a climate scientist and an energy technologist talking to each other, because I knew there was an energy related problem that it turned out he had a data set that the climate people had all the time, but they didn't know there was an energy problem that needed to be addressed. So that wouldn't have happened. The second thing is that I don't have grants in my NSF and DOE portfolio to have my graduate students do anything other than do materials chemistry. And he has funding to do the climate science. But I really thought there'd be a value in students getting cross-trained. And so I've got 2 of my graduate students now who are doing kind of an informal 3-2 program where they're doing 3 years or so, really learning about making better catalysts, but they're spending 2 years doing the energy systems modeling to figure out where are the big holes in the tent that really matter. So then they can be educated in that and kind of combine those 2 skills and what they're going to do in the future. I would personally like to see a whole lot of programs do a whole lot more of that and somehow break down these funding stovepipes that we have. But it's an experiment that I'm doing. So this is Matt Shaner, who was a graduate student in my group. He postdoc with Ken Caldera and me. I was informal as an advisor. Ken was real. We asked the question of, given this data set in a perfect copper plate assumption in the United States of America, moving electricity from anywhere to anywhere, what's the variability in sun and wind together over our entire country? And what you can see is you can see that the wind is variable. Oh, this color isn't showing up here very well, but the light color is the variability of the wind on a given day over 40 years. Okay? There is no way you can do demand management of that. That's not possible. There's no way you can have enough batteries in vehicle to grid to manage that variability. In addition, here's what the number of gaps would be in terms of mean load of the United States ranked in terms of the fraction of mean load that you can't supply as a function of the hours in a year that you can't supply it. And here's where they occur. So now we've got the called LIFO stack, the histogram of how many hours, days, weeks you could not meet demand by 30%, by 50%, by 80% if you built wind and solar to peak capacity to match that peak capacity of current installation. You only have two choices. You can overbuild wind. You can never solve this by overbuilding solar because there's this thing called night. But you can overbuild your wind. Wind therefore becomes more expensive by a factor of the needed overbuild, or you can add storage. Storage, it turns out, is much, much, much more expensive than overbuilding by a factor of 10. So it's worse because although people say, well, when batteries come down to $100 a kilowatt hour, the solar and wind will be the cheapest source of electricity. That's not reliable electricity. That's just within a use model of, if I use the battery occasionally, then my levelized cost would be that. But you pay for reliability. And right now, statutorily, in the United States, electricity has to be 99.97% or greater reliable. You can't plan for more than 1 hour in a decade not to meet demand. If you keep that same reliability as a standard that people value, because we don't want every blackout every week, even for an hour, then you can ask, what's the cost of a wind solar system that meets that reliability? That's what our modeling does. The reason this is so important is because if you're trying a transition path and you still allow natural gas, this is not a problem. Because gas is so cheap and peakers are so cheap, you can fill any reliability constraint you want and reduce emissions by turning on and off your gas plant. But if you've got to meet our law that says 0, then you don't have gas no more. Even gas with CCS is not 0. And so if you don't have gas, you either have to overbuild or store. And here's what this model shows with 40 years of weather data would be the impact of lowering battery storage costs on electricity system costs. Current values are right here. Current costs are right here. You can see that although on the margin solar and wind is really cheap, not if you have to pay for reliability. If you build out solar to be reliable, it costs 3 times as much. Why? Because you've got to build it for the winter when you've got less sun and you don't have a way to seasonally store. Second, you've got to build 12 hours of battery storage more than that, because there are some days, you have a cloudy day, you need 36 hours of battery storage. Used infrequently, because not every day you need 36 hours, but you need those batteries sitting there as stranded assets otherwise. When you look at the whole thing as a system, this is a log scale. You can see that with reliability in place, that energy storage costs of batteries would have to come down to below $10 a kilowatt hour before you got reasonable electricity system costs. The reason is because these outages are long, you need more and more energy used less and less frequently. So you pay in the numerator and you pay in the denominator. You have a double penalty for battery storage costs as a function of meeting these longer and longer gaps of energy that are less and less frequent. Nobody ever talks about this. We have the storage mandates in our state, on and on. They'll be fine as long as you can fill the infrequent stuff with natural gas, but if you take that away, the situation totally changes. We've also asked the question of what happens if there's an alternative and you don't rely only on batteries and you take current costs, and we did this from kind of ecological niche theory. Maybe for short-term storage, you want to use batteries, and long-term storage, you want to do something else, like in our something else, power to gas to power. We converted the electricity into hydrogen, store it in either caverns or in repurposed gas reservoirs, and then burn it in a turbine or a fuel cell. Now, most people say that's stupid because the round trip efficiency of that's 25% and a battery's 90%. Yeah, but the cost of storing energy in a bond of hydrogen is 100-fold lower per kilowatt hour than the cost of storing energy in a lithium battery. So this double penalty doesn't come into play. And we showed that even at current costs, power to gas to power for long-term storage will be much cheaper than batteries and will not even eat batteries lunch. You'll still use batteries for like 3 hours to smooth wind and solar, but no more. It would be foolish to build 8 hours of battery storage. And it's much more cost effective to either overbuild wind or use power to gas to power. Costs always get lower when you employ power to gas to power with a wind only or a solar only or a wind and solar system than when you don't. And yet none of the policies, either nationally from the Green New Deal or in the state, have in it anything other than wind, solar, and storage, which is going to be the much more expensive way. It also says that when you look at what the effect of changing the costs in the future of batteries versus power to gas to power is on the total system costs, that you cross on much more contour lines when you're reducing the power to gas to power costs than when you're reducing battery costs. Which means if you wanted to do technology development that would actually have a cost impact on a reliable renewable system, you're much better off investing money in lowering the cost of PGP than you are in lowering the cost of batteries. I know that that's exactly the opposite of what almost all policies now, because they haven't thought about this from this system level with reliability as a constraint in a purely decarbonized system. So we haven't. There's some other non-intuitive things I won't talk about that we've also looked at nuclear. The reason we looked at nuclear was we're unbiased. I'm not biased one way or the other. And so we actually asked the question within this framework of the nuclear power advocates will say, nuclear is renewables' best friend, because if you don't have natural gas, I'm going to build a flexible nuclear power plant and fill all the supply demand gaps. And if I make it cheap enough, then that'll be a solution. I'll help the renewable people. Some of the other people say nuclear is a threat to renewables because if it gets cheap, we just shouldn't build renewables at all. We should just build all following nuclear and be done with it. I'm unbiased. We asked the question from the real data. If the cost of nuclear were to come down substantially, again, we don't say it will, but if it were, would it complement or compete with renewables? That's a well-framed question, right? Because then you can make policy about whether or not you want to incentivize one or the other, or both as a coexistence into the least cost solution. And the answer turns out, whatever your opinion or bias is, that nuclear never complements renewables. It always eats its lunch. If it ever gets cheap enough to fill, then you're going to run at baseline and you're not going to need any of the renewables. If it never gets cheap enough to fill, it's never cheap enough to compete with them in the first place. And there's only a very narrow region where they actually coexist in a reasonable system. So I don't have a bias as to whether or not society would be for or against one or the other, policy incentives or anything. But it's not true that we should go ahead with nuclear and wind and solar by saying that by doing them both, we're going to both be needed without stranding assets in the system. We really do have to make a choice at some point about one or the other, or pay more than we would have had to pay otherwise because we built a more expensive system than we would have otherwise built. So that's a pretty interesting thing too. So what I hope is, I told you, I hope I fulfill my promise about things you probably don't think about very much, but they're just as important, maybe more important than building the next improved solar panel or the next energy efficiency policy thing. Because I would say if we don't solve maybe half of these problems, that we can't actually get to where we're trying to go. And that's what the real thing we need to do, is keep our eye on the ball, because the Earth counts carbon, it doesn't count what we do. And if our job is to eliminate carbon, we gotta figure out ways to deal with these parts of the problems in enough time to actually do something about it. And we don't have that much time, that means we should be working on that. So with that, I hope it was kind of stimulating and not the same old, but then I did my job. And I'm happy to talk to you guys about anything. So thanks.
So officially we are out of time, but it
No.
sounds like, yeah.
Ah.
Anybody that needs to take off, go ahead, and then maybe we can keep
Yeah.
questions.
The questions are great. I learned from the questions.
So your analysis with the solar, wind, and battery was interesting.
Yeah.
But it was, I guess, a little narrow in the sense that you also have storage, water storage.
Yeah, but there's not enough of that to meet any of these capacities.
Yeah, but there's also a company in California that's making a closed loop system that goes under the ground. They're testing in Bavaria now. That would enable long-term storage.
So the energy density of pumping water uphill, if you pump 55,000 gallons of water up the height of Hoover Dam, you've stored the same energy as in 1 gallon of gasoline. So you probably don't need much more to figure out if you want to think about meeting the real national intermittencies to get reliability about just what volume you would need of water to do that.
I mean, I've seen the designs. The closed loop designs are up to something like 16 megawatt hours.
Yeah, but we're talking terawatt hours. You're talking
more than one.
Yeah, okay, so good. So what I will do is take that as a learning opportunity. It would be good if I got some non-proprietary information on a little more about the volume and the capacity of those designs and how many Lake Superiors would be needed. And I can then project that into, we've done that. So to be fair, we've done it with the power to gas to power. We just took the working gas reservoir capacity of methane, and we said, what fraction of that would have to be repurposed as hydrogen in order to meet these gaps quantitatively? Excuse me. So we've done that analysis, and we know the energy density of methane versus hydrogen, and we know the gaps. So we can do the same thing with water, and we can see whether it's credible that we would need all of North America pumped every hour or something else to meet these gaps. So that would be the analytical way to answer the question. I'm happy to do that. If you give me some information, then I'm happy to crunch the numbers and in an unbiased way, see if it turns out that it's viable or see if it turns out it's not viable. Okay, that's fair.
What's your take on nuclear fusion?
We don't have any materials to build those reactors out of, even if we ever get them to work. That's what I told you in slide 3. Even if ITER works, it'll work for a week. It's not going to be economic, but if it works on a physics basis, it'll break even, produce more power than it put in for a week. But after a week, all of the materials are gonna be decommissioned because they can't withstand the radiation and temperature environments of that fusion reactor for longer than a week. We have no idea how we would make materials that are gonna be permitted in a real plant for 40 or 50 years. Nobody has an idea how to build that thing. Doesn't mean we shouldn't be trying. It does mean that you can't just leave it to the physicists to crow that they had break even in nuclear fusion. That would be a great scientific thing. That doesn't mean that our job is done. Yeah. Go ahead.
Do you know, have you looked at including like the economic cost of blackouts in the model?
Yes,
To kind of see it
exactly.
with, like,
So we run our model several ways. And one of the ways we have a cost, least cost optimization model where we estimate the cost of unmet demand at $10 a kilowatt hour. And we say $10 because that's a few percent of prorated hourly GDP. And we say if it gets more than that, then the cost is so big that people are going to run generators or something because you can't shut down the hospitals, right? And that's typically how people estimate the cost of a blackout. Is their cost of unmet demand is on the order of, I mean, it's $10. We pay 10 cents. We pay, so it's $10 a kilowatt hour. That's what we put in. That if it exceeds, so we're not biased, and we do run this thing at 100% reliability, at 99.97, at 99.9, to see what the cost. We don't want to be biased in our system by just meeting the last 2 hours in a decade of demand, right? Because you could overbuild like crazy and have that stranded asset. No, we're very conscious of that, and that doesn't mean we can't do more, but we don't think that these things, our analysis shows that the conclusions are robust when you include a cost of unmet demand and relax reliability a little bit. But that's a great point. Yeah, good.
Do you think it's reasonable to serve all the heating in like the Northwest or the Northeast and like the Midwest with electricity?
Yeah, okay, so there may or may not be any other choice. If you're going to completely decarbonize the state, for instance, well, look at California. We've got an executive order that says we're going to have a carbon neutral state in 2050. Not just electricity system, that's a law in 2045. Actually, I think the executive order is now 2045, which you'll probably know. If the executive order, it's either 2045 or 2050. The executive order says not just electricity, the state is supposed to be carbon neutral. If you've got distributed natural gas, then there's no possible way to do that unless you've electrified all home heating, except if you renewably make that fuel. So you would have to renewably make your methane. The gas company is really, our Southern California gas, I guess they sponsor this. They're very interested, and they gave me a fellowship for one of my grad students to do this analysis in this, because if you're saying you have to electrify all otherwise home heating applications, you're basically telling the gas company they're a dinosaur and you're putting them out of business. The only thing they could be used for is making hydrogen that they don't think is going to be in home heating in the pipelines, right? So if you totally have to decarbonize, either you need to make renewable natural gas, of which there is a limited capacity to do. About 20 or 30% of the current gas supplies could be made from dairies and biogas and landfill gas. But the rest, you either have to make cost competitively from decarbonized electricity, or you'd have to electrify home heating. But remember, the first slide, energy efficiency pays. So job one is to minimize the need for home heating by getting those envelopes in the buildings so that you don't have to heat or cool it very much. I mean, That's what it's cheaper to save energy than it is to make energy.
Just to sort of follow up on her comment, with respect to the heating the Northeast and the Midwest, we already have a lot of seasonal storage of natural gas,
Yeah, right.
which can then be tapped into. If that's replaced someday by gas or some other form of energy from renewables, we'll still need that large amount of storage space, even for heating, leaving aside the grid reliability.
Yeah.
So it sounds to me like if we kept that pattern, we would have that capacity that might serve more than one purpose.
Oh, yeah, that's right. And there's no bound, it's just a cost bound now. You know, the 4 trillion cubic feet of working gas we have, we could in principle make 8 trillion. It's just whatever they store enough now to meet seasonal storage needs of methane, but could store more without making salt caverns. We could put them in the geologic reservoirs right now. And we're depleting oil and gas reservoirs all the time, opening up more storage.
Yeah.
In a way, like this is what your talk was about in its entirety, but I was wondering if you had a more direct answer is completely decarbonizing the right goal? And if not, or you're not sure, how can we find the right goal?
Yeah, right. Okay, so that's a very perceptive and great question. The right goal depends on whether you're optimizing based on economic value and productivity, or you're optimizing based on what you perceive is an existential threat based on carbon emissions into the atmosphere. Those are two different things, right? If you think that it literally is an existential threat whose chance of mitigating in the one shot that we have is now, then you optimize your chances of success as opposed to minimizing your chances of failure. If you think that it's something that's nice to have and you optimize based on economics, you know, you start to say a very different path of maybe cost effectively, we should get to 50% emission reductions, and whatever climate damages, they won't exceed the savings that we would have otherwise spent to do more than that. You end up with an unknown unknown. You have no quantitative way to evaluate the sign or magnitude of climate damages. And given that we don't know what the technologies will be like, we don't know what the costs of mitigation are actually going to be. So we don't know the cost, and we actually don't even know the signs of the benefits. And so you end up in a very difficult economic optimization condition. My one-line slogan on that, probably from Yogi Berra, is, you know, when you come to a fork in the road, you just have to take it. Right? So I didn't think that quantitatively answered your question. I gave Tom Friedman, if you read Hot, Flat, and Crowded, I'm very proud. I was Tom's teacher. He acknowledges me in that book all over the place. I had several lines. And I gave him a line that he actually used a lot. Actually, we're streaming here.
I can turn you off.
Yeah, but it's so you can turn me off.